obviously, Halloween was probably less than optimally done this year. Normally I try to at least have a little more fun with class around those days, but in absence of time, energy, and physical practicality of that made it a little harder. But I don't want you guys to miss out on at least something I usually do every year. So I'm going to wipe off this table. And still gonna have some candy. Come up yourselves at any time, just try to leave some for the next lecture too.
Yeah,
There's some fruit and some chocolate up there. I try to cover the bases.
no one else can.
I wiped off the table and it's there 6 feet away from anyone, so y'all take your time at your leisure. Let's see. So, moving to slightly less fun things probably is the fact that we do have a test coming up. Much like last time, it is available for you to take at any time between today and the end of next Monday. What that means is, when you are ready for it, you send me a word and I will send you this document. Today, we're going to be talking about that test itself, going over the information that I already gave out this week, answering any questions you guys have, specific questions that you encountered while studying. And since today and tomorrow are going to be entirely focused on test and review, if you don't feel that you need review, if you feel comfortable and just want to be studying on your own or sleeping, then you are not required to physically attend class today or tomorrow if you feel like you are okay with this test and don't need anything. That said, I will be here. I'll be people studying review. I'll be in here for class today and tomorrow. And additionally, since we don't have any labs this week, I will be in this room when lab would normally be 1:30 to 4:30, just in case anyone comes in with a study question. Additionally, if you wanted to take your test physically with me in the room, that would be a good time to do it, because I can be here and you can really quickly get feedback. And I want to give you guys as many options as possible. Additionally, I've had people, like the last test, I had some people come in during the Friday lecture to take the test then in person just because they wanted to. So those are options for you. If you prefer to take it in person just to be able to get more immediate feedback, if you think that would be faster or more efficient for you, that is an option for you. I'm just rambling already. So before we get too far into it today, how are y'all doing? And any big pressing concerns that you guys have before we just start reviewing material? Yes?
What will be the format and the days of the exam?
Oh, the exam at the end of the semester?
Yes, sir.
Well, so I'm pretty sure our exam days stretch from Sunday through, I think, maybe Wednesday at maximum. I think this class has 2 exams. Come on. Now, okay, if you're asking about the exam itself, my exams are basically just longer tests. If you're accustomed to the way that I've been doing tests, you have so many questions, a couple on each page with a number of points attributed to it, and I grade pretty heavily for partial credit. It'll work exactly the same way, but mechanically the actual document will work very similarly. Each question will tell you how many points it's worth, there will be more than 100% worth of points on it, etc. As for the when and the how, I believe the way PC is doing exams right now, the information exists, it's just not on the top of my head. Exam days are the 22nd through the 25th of November, and I think, because I have 2 lectures of this class, the 2 assigned days for it are the 22nd and the 24th. Now, because my 2 lectures are exactly the same class, I really don't care which one students come to. Now, I'm still working out whether or not the exam can be in person or not. But I like to give people that option if they prefer it that way. Also, it's harder to take an exam remotely where you can't get immediate feedback on all of your issues. But there's so probably leaning towards in person for that one, just to be able to help you guys immediately with your questions. But obviously, an online option will be available for those who need it. Details and finalizations to follow. But if, for at least an in-person version, I don't care between these 2 days, the 2 assigned slots for this class, which one you attend. I'm giving the exact same exam twice to 2 different groups of people. So if one works better for you than the other, go ahead and do that. Additionally, if I was doing it online, I probably wouldn't care when you take it from your days at all. Like, I'll give you the range of days and you can choose your time. I'm still needing to get some information about exactly how I can do the exams. If it's in person, I don't care which time slot you take. If it's remotely, then you can take it at any point during the exam days. More information and finalizations will come very shortly. Thank you for reminding me to chase that information down, what exactly I'm allowed to do. But those are coming up at the end of the month. This week and weekend will be test 2. Then we will spend about a week or so on a couple additional topics, and then about a week on exam review. Nearing the end, y'all are doing it. Y'all are making it. Any other, I guess, structure questions before we get into content stuff? Pleasant Halloween all around, I hope, at least. If not optimal, at least not awful. I believe it was Halloween and voting this weekend. Okay. I need water to live, but for some reason, water makes me choke more than food does. I drink water, it makes me choke, and then I eat food to fix it. Something is wrong with me. Okay, lots of things are wrong with me, that's just one of them. But, yeah, I guess it was Halloween and voting the same weekend. That's the same stretch of 5 days. That's pretty action-packed. We all need a vacation. Well, one is coming, at least. A nice, long, about 2-month one, which I'm looking forward to. Okay, so I'm going to pull up. I'm on Brightspace. Every time I leave Brightspace alone for 5 minutes, it's like the end of it. Use some back in. Okay. So on Brightspace, just to go over where everything is again. Scroll down here, past the Chapter 8 tab, we have the Test tab. We have the formula sheet. This is just the formulas from Chapters 5 through 6. These are the only ones you should need. Sorry, 5 through 8. 5 through 8. Excuse me. And they are sorted by chapter, if that helps your flow of logic at all. This is every formula that you could possibly need. So the other formula sheet from the first test won't be required for this one. We'll also eventually post an exam formula sheet, which is just the two of them combined. This particular sheet doesn't itself contain like tables of constants, but any question that requires a table of constants, like involving specific heat or thermal conductivity, those constant tables will be next to the corresponding question on the test itself. I can't show it to you, but if a question requires such a table, it is there localized with the question. So you don't need to worry about a separate document for that. But this is on the website. You can print it out, mark it up, access it here anytime. Then we have practice questions, which are excellent review. Again, they don't match the test perfectly, but if you can do these, you can do the test. And we have the answer key to those questions. As I said last night in my email, I realized that the scan quality here isn't great. I'm going to try to use different colored inks to make it more visible, but the scanner that I had to use only did grayscale and very poorly at that. So immediately after this lecture, I'm going to go scan it again with the nice expensive office printer to make it look nicer, and then I will replace these 4 separate pages, PDFs here, with one page, with one document that contains all 4 pages in visible red ink. But presently they are here. I'll be using them to check your answers to these questions. Now, we also had to do the Chapter 8 assignments were due on Tuesday. Those seem to go pretty smoothly. So, any specific Chapter 5 through 8 content or questions, or maybe specific questions from these practice problems that you guys have at this time? If not, I can just go through things generally. Any specific question at a time, please immediately let me know. So, there was another piece of information I wanted to say. So everything in this tab is good for you to use while studying. If you click on the tab itself, there are instructions for the test and also the list of things that were contained within Chapter 5 through 8. Watch the video that I sent out Monday for you to watch Tuesday, then that is me going through this list, so you can refer back to that if you need to. If no one has anything specific, I'd like to go through these questions with you and briefly talk about the answers. Just because again, if you can do this, if you understand this, you'll be good on the test. I always try to make this longer than the test itself. So, I begin with some brief content questions. What is thermal energy? It's basically just kinetic energy on the atomic scale. Again, we define energy not as, our best definition for energy is just a thing that matter can possess. And when matter possesses thermal energy, its particles move around and jump around and collide more. Methods of heat transfer, they are conduction, convection, and radiation. Conduction requires touch. Convection requires flowing fluid mediums to transfer the thermal energy. And radiation uses radiation, which can be defined as light or any other type of electromagnetic radiation. This is a brief preview of what we will talk a little bit about next week. But, since I opened Pandora's box there a little bit, because I find it interesting, this is the electromagnetic spectrum. This is every single type of radiation, barring, there's one more type, cosmic, which is like gamma but scarier and from the bowels of space. All of these up here, radio waves, sorry, that's not an M, that's supposed to be a symbol for micro. Radio waves, microwaves, infrared, light, UV, X-rays, and gamma rays, these are all technically forms of radiation, which means you are being irradiated right now by literally the light from these lamps. But not every light, not every form of radiation is the type that makes the Incredible Hulk. Some of these forms of radiation are completely benign and have no effect on human beings. Things like radio waves literally do nothing to you. Light only interacts with your skin and the photosensitive cell of your eyeballs. Some forms of radiation do pass through your body and can cause damage, like gamma rays and gamma waves and X-rays, but they don't all do it. They are, including light, they are all just different types of the same thing. Radiation is basically just energy traveling as a wave, and because it is traveling energy, something can absorb it in the form of thermal energy. And oftentimes, when something absorbs any form of this radiation, it's going to get some thermal energy from that. Light and all of its cousins over there are just different types of the same thing, traveling energy. And that means that any form of radiation you give off is giving off some form of energy. As a specific example, infrared goggles or night vision goggles, the kind that you put on and you can see like a person outlined in red because of their heat signature. For those goggles to work, your body has to be giving off energy via radiation. You are radiating right now. You are technically radioactive. Your body is currently reflecting light visibly, giving off its own native infrared radiation, which is the reason why the infrared goggles can see warm-blooded creatures. You're also giving off about 1 gamma ray every single second, just due to the natural radioactivity of the calcium in your bones, which is entirely, your body knows about that and is able to tolerate it. Not all gamma rays are bad. It's only, like most things, it's only bad in high doses. I just like talking about this, and it's going to be one of the things we do cover next week, just in the additional topics section. Then converting temperature scales. We start from 100 in each scale, and then just convert it into its appropriate other scales. Just make sure you are able to do this. And laws of thermodynamics, very important. There are technically 4 of them, 0 through 3rd. Basically, the law of thermal equilibrium, energy conservation, entropy, entropy of the universe as a whole, entropy of single objects, and your temperature right now. Now, I've gotten some specific questions about some of the math on the next couple of pages. You know what? I realize that this is probably hard to read. I will put this version up. Is that easy? That's easy to read? Easy. I know this projection resolution isn't great. PowerPoints, the words are just bigger. There we go. Okay. So the first page of practice questions, and similarly the first couple questions on the test, are going to be sort of concept driven. So make sure you're familiar with the concepts mentioned. Just add, here they are. 5 through 12 are all math questions. Number 5 is kind of it's basically just a really long, drawn-out conversion question. And this is how the human body works in a way. Average human adult uses about 230 joules every single second. So every moment you are awake and not laying still on your back, you are using energy to do various things like breathe and move your muscles and think. Thinking does take energy, actually. Not something you think about, but you do burn calories by using your brain. And all humans use some amount of energy every single second. So 230 joules per second is actually your wattage. It is the power that your body acquires every single moment. If you have less energy than this burned every single second, then you're not getting enough power and you're probably going to fall asleep. And similarly, every single piece of food we eat contains a specific amount of energy inside of it, which means that every single piece of food you eat is able to keep you awake and functioning for a specific amount of time. Your food is basically you're just eating batteries. Now this particular question, we were first told energy per pizza slice. So calories, this is big C food calories per pizza slice. And these are the units you're starting with, calories per pizza slice. But what we want to eventually find out is time per pizza slice. The time that one pizza slice can keep you awake and functioning. So ultimately, we want to cancel out calories and replace it with time in seconds. So the way that I do this is really just sort of a long conversion chain. We know the conversion between calories and joules. Go ahead and fill in that blank. 1 calorie is 1,186 joules. If you've been paying attention, you probably noticed that this particular number shows up a lot. And it's because it was based around water, or as a specific heat of this much. A lot of units in physics were based entirely on the properties of water. And then the joules per second number is also basically just a conversion. It converts joules into the number of seconds that you can keep awake. So this chain of events will cancel out calories, replace them in seconds, and will tell you seconds powered per pizza slice. And the answer comes out to be, like if you convert to seconds, you get into hours, about 1.5 hours per pizza slice. So, assuming this is an average size, like medium pizza or large pizza slice, that means that one whole Little Caesar's pizza can keep you awake for a whole day. Not including garlic, not including crazy sticks. So, you can work this like a conversion, which is just how my brain does it. Additionally, you can also do this with the power formula, because that 230 joules per second is power. Joules per second is watts. So that's the power rating that a human being requires. So you can plug the 230 in here. And the work is the energy you use. So you figure out how many joules are in one pizza slice. That goes here. Solve for time. So 2 ways you can think about this one. I get a lot of questions about these types of questions because it doesn't technically have, you don't have to use a specific formula. It's just a series of conversions one after the other. So I have given you every formula you need, but technically, not every problem always needs one. That's conversion. Yes?
How would you compare this test to the first test? Which one is more difficult?
I probably would think this one would be a little bit simpler, because we included a lot of stuff on that first test. And some of it were things like rotation and torque and centripetal force and gravity, the universal law of gravitation formula. Test 1 was just packed because there was just a lot of those movement basics that we were covering before we shifted gears into this stuff. The scores on test 1 were really good. You guys did very well on test 1. And as long as you've been following along your notes and doing your homework, and I have seen that you guys have been, then I'm absolutely not worried about any of your scores on this particular test. I think this one's probably a little more concise. There's really only 2 halves to it. You've got the pressure half and the heat half, as opposed to like 3, 4, 5 different chunks of the first one that are only tied together by Newton's laws. So I would think this one would be probably a little more straightforward. There's fewer formulas at least. Does that answer your question? Anything else? Okay.
Can you go over like conductivity?
Yes. Well, let me pull up notes from thermal conductivity. And we can work the conductivity question in this as a sample. So, as a review, there's 3 methods of heat transfer, and you can give off energy via radiation. You can just let energy flow via convection, but the most straightforward way is 2 things are physically touching each other. Thermal energy will conduct from one to the other. And the various factors affect the speed at which that energy will transfer. For one thing, the material that the objects are made of will affect the rate at which thermal energy is going to flow through it. I'm going to draw a comparison to electrical conductivity. Different materials allow electricity to pass through them at different rates. Metal conducts electricity very well, rubber does not, which is why we coat most of our wires in rubber so that we don't electrocute ourselves. What something is made of affects the rate at which things will conduct through it. And heat conducts very similarly to electricity. It just moves from atom to atom from one side to the next. And oftentimes, if something conducts electricity very well, it will probably conduct thermal energy very well. If you look at this table up here again, this chart lists the thermal conductivity constant for a bunch of different stuff, and the metals category overwhelmingly conducts heat and also electricity the best. All the conductivities drop very strongly when you come down here. A common statement is that water conducts electricity very well. So you might be surprised to see that water conducts heat very poorly. Water is a very good thermal insulator. It does not allow thermal energy to pass through it very quickly, which does disagree with the statement that if you conduct electricity well, you should conduct heat well. The thing about water is, water, pure H2O, does not conduct electricity very well. Water conducts electricity when there's things dissolved in it. And it's those dissolved particles that are conducting the electricity. Pure H2O is really bad at conducting electricity. Granted, most water has something dissolved in it, so that's why most water seems to conduct electricity, but pure H2O doesn't, and that's a tangent. My brain likes to leap from things. So, what something's made of affects the rate at which thermal energy will be transferred through it. That rate is basically just we call it the thermal power, because power is energy per time, which is the rate at which energy is flowing. So, first formula is thermal power is heat flow over time. If you have a specific object that thermal energy is passing through, let's say, for instance, like a glove on your hand. The whole point of the glove is to try to keep your hand warm, or to keep it from getting cold, or sometimes to keep your hand from getting too hot, depending on. The point is, the glove tries to keep your hand at the same temperature. You want it to be comfortable, and you don't want a massive change in the amount of thermal energy in your hand. So thermal energy will pass through the wall of the glove in a certain amount of time. That's the thermal power. We also call this heat current. We can also call this just a rate of conduction. There's a lot of synonyms here. And what it's made of affects this. Gloves tend to be made of things like, well, there's no entry for like wool up here, but wool is made of carbon. Wood is also made of carbon. So as a benchmark, I would assume like a wool mitten would be not dissimilar to the conductivity of wood. But this is your first formula. Again, just power is energy over time. I realize I never really acknowledged this piece right here. This symbol isn't an equal sign. this symbol is a like approximately or similarly to symbol. It means that this does not equal this, but this is proportional to this, which means that the flow of thermal energy is proportional to the surface area, the change in temperature, and the length. So this version of the formula here isn't complete. It's missing the K piece, which is why I'm not grading you on this part. This is not on the formula sheet. This piece here is not something you need to use. It's just sort of the in-between between these two things. So I'd say your two formulas to focus here on are just this one, which is the same power formula we've been using, and then this one. This is specifically thermal conductivity through a specific object, and whatever your object is, it's made of a material, therefore it has a thermal conductivity constant. You look up the K value for what that object is. It also has some cross-sectional surface area. If you were just looking at a rectangular wall, you'd find that area by multiplying the length times the height. Just, again, area, geometry. And dividing it by the formula uses the term length, but it's really the thickness. Like if it was a wall, it'd be the thickness of the wall, the distance the thermal energy has to travel. Yes.
So L is thickness?
L is thickness. You can perfectly adequately refer to L as thickness. Granted, if you were looking at thermal energy through like a wooden dowel, then, like if this was your hot side, this was your cold side, then L would be length, just the distance from one point to the other. So whether or not it's length or thickness kind of just depends on the object and your perspective. But the best definition is the distance the heat has to travel. And then A is the surface area it is going to travel out of. So for this wall, it's just the surface area of the wall. For like a wire or something cylindrical like this, it would be the area of this circle on the end. It's always the cross-sectional area of the surface that the thermal energy would point in straight arrows out of. The area it passes through. It's kind of like the size of the door. Yes.
What is K specifically stand for?
K refers to these. K is thermal conductivity constant. So on your notes, K is thermal conductivity constant. These are Ks. I'll even probably, you know what, I will put on the test a big old letter K up there. This is K. It refers specifically to this table, like how C refers to the specific heat table. K is this variable. It's where you factor in what the thing is made of. And again, this part here is missing it, which is why it's not a complete equal sign here. Power is proportional to area and temperature change over length, but it's not until you factor in what the object is made of that you actually get the real answer. So power is equal to what you're made of times the area that the heat travels through times the temperature difference between the hot side and the cold side divided by the length, the thickness that you have to travel through. Now, we already did the question and notes together, but I am going to pull up the sample question. Here. So, sample question number 9 on the practice test is a thermal conductivity question. Look at that briefly. We are told about a blizzard, and you take shelter inside of a wooden shack. The walls are made of wood, that's important to note. fact that the walls are wood means we need to look up the thermal conductivity of wood, which is on the table in the notes. And I just remember from looking at it a second ago that the specific conductivity is 0.10, and units there are joules per meter per second per degree Celsius, I think. So walls are made of wood, you have the thermal conductivity of wood. The inside of the cabin, which if it's a blizzard, that's the hot side where you want to be, 25 Celsius. The blizzard temperature outside is negative 15 Celsius. I think that's bone chilling temperature, especially if there's wind. Well, there's solid wood that are 10 centimeters thick. So since they are this thick, that's the distance the thermal energy has to worm through in order to get from one side to the other. So this is your L. And the walls have a surface area of 9 meters squared. So that is the area of the wall. If you were to measure length times height and multiply them together of whatever wall this is its surface area. And the first thing we are asked is, what is the rate of energy lost through the walls? This is something architects have to deal with a lot. If you want a building to stay at a comfortable temperature, you need to make sure that the thermal energy level inside doesn't change too much. So in the winter, the inside is the hot part, and you don't want thermal energy leaching out through your walls. In the summer, you want the inside the cold part, and you don't want thermal energy leaching in through your walls. Which is again why we make them out of things that don't conduct heat very well, like wood and insulation, instead of thin sheets of metal. But we are asked for the rate of energy lost through the walls. Rate of energy transfer, so that is the thermal power formula, which is on the screen. I will rewrite. Power equals K times A times delta T divided by L. And we know all of these variables. We know what the wall is made of, area, temperature difference, and thickness. So all we have to do is plug things in and get started. Power is equal to 0.1 times our area times our temperature difference. Notice it's not really final minus initial here, it's hot minus cold. Our hot temperature is 25, our cold temperature is negative 15. Since this is basically a delta T situation, you can use Celsius and be fine. In any problem, typically the best thing to do is use Kelvin, but this is one of those cases where Celsius will also work. So ultimately we're going to have 25 minus negative 15 because there's a difference between those two temperatures of 40 Celsius. And then divided by length. We're given length as 10 centimeters, but all of our questions will take meters unless otherwise stated. So 10 centimeters is how many meters? Very good. One. And we are now good to solve for power. Something to make note of here is sort of the order of operations for how you put things into your calculator. Because if you put all this in at once, haphazardly, the calculator might try to divide only the negative 15 by 0.1. Make sure that you put everything in one at a time and surround it like similar like terms in parentheses. Don't remember the answer, but I'm going to pull up the formula sheet, the answer sheet real quickly.
So how are you supposed to answer it?
It is 360, correct. The answer is 360. And if I was putting this into a calculator, the way I would do it is, well, 0.1 open parentheses, 9, close parentheses, open parentheses, a second open parentheses, 25 minus negative 15, close parentheses, then division, 0.1, then close that parentheses. This way, if order of operations, you always do parentheses first. This term is by itself. Within these parentheses, you have two terms. So we look at the ones inside the parentheses first. The calculator should do the 25 minus negative 15 first. Then divide all of that by 0.1. Then start multiplying that by the other things. So the sort of extra set of parentheses here is the important part. Now, I think this one's sort of one of the lower stakes ones. I think there's fewer mistakes a machine could make with this one specifically, but again, good practice to help other issues from coming up later. And the answer you should get is power equals 360 watts. So that is the power loss through the walls of this particular cabin. And the second part of the question asks, how much thermal energy do you need to produce each second to counteract this loss? 1 watt is equal to 1 joule per second. So every single second, this many joules are exiting your cabin. Which means if you want to make sure you maintain the exact same temperature in your cabin during the entire blizzard, you need to then, like your heater, whatever device you are using to stay warm, needs to be producing 360 joules of thermal energy every single second to make sure that the temperature in the cabin does not slowly drop over the blizzard night. Which is why we have heaters in our houses. You want some device to make more thermal energy to counteract whatever you lose through the walls. Thankfully, the human body is also basically a furnace. You do make some of your own thermal energy, but just to avoid a hypothermia scenario, bring some source of heat anyway. Any other specific questions? Okay. We are nearing the end of my normal lecture time, so I don't want to keep you too long. But again, please do just look over these as good study questions. A specific question I've been getting about one of these practice questions is number 8. This is a Q gained equals negative Q lost type situation. You're adding hot water to cold water. And even though both objects are water, they're still technically two separate objects. The hot water is going to lose thermal energy, the cold water is going to gain thermal energy. So this is a Q lost equals Q gain situation. You've got two separate sides and two separate amounts of water on each side, losing or gaining some amount of thermal energy. Yes?
Did we get our logs out?
Which ones?
Or the ones we did last week?
So a weakness I have as a professor is grading labs in a timely manner, which is a weakness of mine. It's entirely my own problem, my own fault. And as a result, I'm just behind on lab grades. And I do feel bad about that. It's the way I prioritize my work order ends up happening. I am going to try to be getting them to you as quickly as possible so that you have a better idea of what your grades are during the semester. But it's just something that's going to take time. I try to do them from in the order they were assigned. So last week's would be the one you get last. Sorry. There is the first several paper labs here. I'm going to be getting into the online lab shortly. Do remember you can come collect these, and if you want to know what the grades I have the credit recorded are, like if another lab partner of yours happens to have claimed the paper one, I can tell you your lab grades. I have them all saved in the spreadsheet. spreadsheet. I'll be getting through more of them soon, so sorry for the delay there. Anything else?
So these are the ones we can grab right now?
Yes, absolutely. They're yours to keep.
Okay.
And if you don't see your name, the laptop that might be taking it, if you don't know. So, restudying, let me know any questions you have while studying. Taking the test remotely, send it when we're ready to start. I will be in here offering study help during what would be normal lab times and during class tomorrow as well. Thank you all very much. Have a good day, study well, and stay safe. You know, hopefully you know that. Y'all got this.
I have a question about
Okay, so this particular formula, force buoyancy, force buoyancy, for some reason, force buoyancy equals density times volume times gravity. It is density of the fluid that you are floating in. In this case, it's water. That's 1,000 gram fluid.
So we need to know that.
I should have put that comment.
Well, okay, but like, that's not. So it's 1,000.
Right.
And then 0.11.
That's sorry, that's not 0.11.
1.1.
That is 1 times 1 times 1.
Okay.
That's calculating the volume of the cube.
Because it's a cube. Okay.
Right.
Sweet. So, okay, got it. Thank you.
Go on.